In this episode, I would like to tell you a few words about color management. Here we have the option to turn color management on or off. But what is color management? Should we turn it on or should we turn it off? Should we care at all? If the monitors displayed the images exactly as they get them, we wouldn't have to worry about this at all. But unfortunately, it is not so. And it all starts with good old CRT monitors. There is a technical issue that is related to voltage, to some physical aspects that I will not even try to explain here. It's nothing interesting from our point of view. The only thing that we need to know is that the monitors darken the images. So if the monitor gets the image like this, it will display something like this. The relation between the image that gets to the monitor and the image that is displayed on this monitor can be described as such curve. So that's what we would get. So how come that we see the images as we want? It's because this error of the monitor is well known, and it's not that difficult to compensate for this error. So the original image is encoded, is pre-brightened before it goes to the monitor. The opposite curve is applied to this image. If this is our intended image, it's encoded like this, so we get this image, a lot brighter one, and this is in fact what resides in our computer. This curve is burned into the image. Then such image goes to the monitor, monitor applies its error, so we get this. And that's exactly what we intended to be displayed on the monitor. Those operations go under the hood. We may not even know that those things occur, but we see correct images on our monitors. So what's the problem? Why should we even care about those things? Those are just some technical issues that, as we can see, have been solved. And we don't have to worry about them. It's true, but only to some extent. Say, for example, that we shoot this image with our camera, and we would like to double the exposure. What does it mean? We simply allow twice as much light to reach our sensor. Let's mimic this by multiplying this image by 2. So I will add the color mix, change the blending mode to multiply, feed the upper socket with the image, then the lower sockets with the values of 2 for each channel. So this is making the exposure twice as high. And when we do it in camera, we would get such image. Now let's imagine that we would like to fake this effect in computer. When standard approach is used, the algorithms that are used in Photoshop, GIMP, After Effects, in editing systems, we would get this instead. As you can see, this image doesn't look the same as this image. This is the real world behavior, and this is what we get when we use a standard approach to adjusting the images in most of the applications. The reason for this difference is this curve, which is burned into the image. So we are in fact working not on the images that represent the real light intensities, but on images that are a lot brighter. If only we had a chance to make our modifications here before this curve is applied, we would get the real world behavior. But this is impossible, because the curve is burned into the image. This happens before this image goes into the application. So is there any way to cope with this problem? Yes, it is, and it's called color management. Color management is forcing the application to adjust the images when working in linear color space, which means in color space that represent real-world light intensities. But the application can work in this area, from this point to this point, because all this happens before the image gets into the application. And this is what happens in the monitor. This curve is burned into the image. So what can be done to reverse this? The opposite curve can be applied, like this. But as you can see, we destroyed the result that is displayed on our monitor. But that's not a big problem, because we can gamma correct this image again before it goes into the monitor. And this is what color management does, leaving the user this area to work with. So now, when we try to mimic to double the exposure, we multiply our image by 2, we get this result, which is exactly the same as the real world results. Because now all of the operations, all of our adjustments are performed in linear color space. So again, this is the image that we intend to be displayed on our monitor. In order to make it possible, certain gamma correction has to be applied. It's applied to this image and those informations are burned into the image. And this is our file. When we don't enable color management, all of the operations are performed on such images. Then the image with all of the adjustments that we applied to it using non-linear color space goes to the monitor, which darkens it, so we get something like this. When color management is activated, those things happen anyway, but when the image goes into the application, it's been decoded so that we have the linear version of this image. Then we perform all of our operations. The result of them is encoded again, and this image goes to the monitor darkens it, so we get the result that we want. This is our field of operations. This is where the user can play. Those things are done automatically by the application when the color management is turned on. And those things here in the monitor or here where the initial gamma correction is applied to the image are completely out of our control. So now when we know all those things, we will never again wonder why we get different results in Blender and let's say in Photoshop when we apply exactly the same adjustments. The reason is color management. Photoshop doesn't use color management. Blender has color management turned on by default. If we don't touch it, we will be working in linear color space, so the results will be different. I encourage you not to touch this thing. When we get used to this behavior, we can really achieve more realistic results than if no color management is used. We are creating our world in 3D. We are faking the behavior of the light. We will be mixing render passes together, passes that represent the several lights, several lamps that we place in our scene, the energies of the lights. So it's logical that when we add the energies of several lamps together, we should get the sum of all of those energies. And this is possible only when we are working in linear color space, the color space that mimics the real behavior of the light. There are, however, scenarios where we don't want to use color management. Or something a little bit more difficult, mix color managed images with the adjustments performed on gamma corrected images. In such cases, we would have to do something like this. Let's first get rid of all of those nodes because we don't need them any longer. All of those adjustments are being applied to our image anyway because we have the color management turned on. And now say we have all of our setup in linear color space and we would like to mix some results with non-linear adjustments. When we use the input image node, here we have the linear version of this image. So if we want to perform some operations on non-linear version of this, we have to apply the gamma correction curve. And fortunately, we don't have to do anything like this. It's impossible to be precise using the RGB curves. So instead, we will simply use the gamma node. We can pass this image through the gamma node and enter the value of the gamma. In most cases, we are dealing with images that are encoded as sRGB color profile. Blender assumes that everything it gets, every file like JPEG, PNG, TIFF, Targa, that those images has sRGB color profile. And in most cases, it's not mistaken. sRGB is gamma of approximately 2.2. So this is what I do here. I simply pass the image through the gamma node and enter 2.2, which is in fact exactly opposite from what I wanted. So let me simply add the converter math node and here I will type in 1 and I will divide it by 2.2. So I will change this one to divide and I will feed this one with this value. Now I have the gamma corrected version of this image. So exactly the image that resides on our hard drive. Then I do all of the adjustments that I want to apply to this version of the image, the curved version of the image. So let's maybe do something like this, just for fun. And then I have to reverse this process. So let me simply duplicate this node, drop it here, and apply 2.2 gamma. Let's mute this node, and let's see. This is the original image. And this is the image that goes through the gamma node, where I set the gamma to 1 divided by 2.2. This node is muted. And here I pass it through the gamma of 2.2. And as you can see, those images are exactly the same. But here, when I perform anything between this node and this node, I am doing my operations on gamma corrected image. So I can mix those weird things with all of the adjustments performed on properly interpreted footage in linear space. So this is how it all works with the images that come from outside. We can use some images, some PNG, JPEGs, TIFFs, or whatever, as the textures. In such cases, we should definitely use color management. When we use the image as the texture, apply it to the material of the object, and we use the lights, which is rather obvious, we would like the colors of the texture to react to the light in a natural manner. And this will happen only when the color management is turned on, because the gamma corrected image will be decoded. So the texture will use the linear version of this image. This will properly interact with the lights. Then the result of everything that we do will be encoded again so that it's properly displayed on the monitor. And colors that are used in materials. When we have the color management turned on, those values of RGB represent the real light intensities. If we turn the color management off, those values represent the gamma corrected values. You immediately see that the same values now represent darker color. So that would be all in this episode. Please treat this as just an introduction to color management. I encourage you to get used to working in linear color space. Getting used to it gives us the chance to achieve better, more realistic results.